All right, everyone, get ready for a deep dive. Today, we're tackling solid-state chemistry.
Yeah, the stuff that makes up, well,
Pretty much everything.
pretty much exactly.
You've got these awesome lecture excerpts to break
Yep.
down. And honestly, you won't need a PhD to find this stuff fascinating.
No, not at all.
We're going to uncover how atoms arrange themselves in solids, kind of like,
Like microscopic Tetris.
exactly, like tiny Tetris. And we'll see how that impacts a material's properties.
Yeah, what's really cool is how often we just don't even think about the solids all around us.
Right.
You know, phones, buildings.
Little bones.
Exactly. Our bones are solids, but when you understand their structure at the atomic level, it unlocks so much.
It's like a whole secret world, right?
Absolutely.
So let's break down these lectures. They start by classifying solids into four main types: metallic, ionic, covalent network, and molecular.
Right, like sorting Legos, but instead of by color,
It's by how they bond.
exactly, how they bond together. So cool. And then one of the first things they jump into is this idea of close packed structures,
Yes.
which is essentially atoms trying to get as cozy as possible.
Yeah, they're like little puzzle pieces fitting together.
Yeah.
Imagine stacking oranges at the grocery store. You want to minimize that empty space.
Efficiency.
That's it. Efficiency, even at the atomic level.
Wow. And the lectures talk about two common ways they pack: hexagonal close packed, or HCP, and cubic close packed, CCP. So are those like different stacking strategies for our oranges?
You got it. Two efficient ways to arrange those spheres.
Okay.
But here's where it gets even cooler. Even when they're packed super tight, you still have little gaps.
Oh.
Little holes, like those air pockets you get with the oranges, just much smaller.
So even when atoms are all up in each other's business, there's still some breathing room.
There is, yeah.
Huh. Are those holes important?
Super important.
Right.
They're not just empty space. These holes determine where other atoms, especially smaller ones, can fit in.
It's like having different sized Lego bricks. Some fit in the big gaps, some fit in the small gaps.
Right.
And this is key when we talk about things like alloys.
Okay, alloys, like the stuff that makes our stainless steel shiny and rust-free. Tell me more.
Right. So think about it. Many metals naturally love these close-packed arrangements.
Okay.
That's their happy place. But we can mix things up a bit by adding in other elements. And that's how we create alloys with unique properties.
So we're spicing up the metal world, adding some atomic flavor.
Exactly. And the lectures talk about two main types of alloys.
Okay.
Substitutional alloys, where atoms of one metal basically sneak in and replace some of the original metal atoms in the structure, like swapping some of our oranges for grapefruits.
Okay.
Brass, for example, you add zinc to copper. That substitution gives it that lovely golden color and makes it stronger.
So substitutional is swapping atoms. What about the other kind?
The other type is called an interstitial alloy. Here, we're taking smaller atoms and squeezing them into those tiny gaps, those holes we talked about.
Oh.
It's like tossing some blueberries into our fruit basket.
Okay.
A classic example is carbon steel. Adding a tiny bit of carbon to iron makes the steel much stronger because those carbon atoms get in the way of the iron atoms moving past each other.
So it's like reinforcing from within.
Yes.
It's amazing how just a pinch of another element can change things so drastically.
Yeah, it really is. And think about stainless steel. Adding chromium creates a protective layer that prevents rust.
Right.
The chromium reacts with oxygen to form a shield. So, by understanding how these atoms fit together in alloys, we can literally engineer metals to our liking.
So we're like atomic architects, designing with a purpose.
Exactly.
That's so cool.
Hey.
But are all solids built around these close-packed structures?
Not all of them, no. The lectures also talk about other fascinating types of solids, like ionic solids,
Okay.
which are all about electrostatic forces, positive and negative charges attracting.
Like magnets, but teeny tiny.
Exactly, on a much, much smaller scale.
So ionic solids, they're all about those positive and negative ions attracting each other. Are these solids as tightly packed as metals?
Not necessarily. It all comes down to their size and charge. Like, imagine you're trying to fit different sized balls into a box.
Okay.
You get different arrangements depending on what you're working with.
That's like a 3D jigsaw puzzle.
Exactly. And one of the tools that helps us predict how those ions will arrange is something called the radius ratio. It's basically a way to compare the sizes of the ions.
Gotcha.
And then we can figure out how many neighbors each ion can have.
Neighbors, like how many other ions it's bonded to.
That's right. We call that the coordination number. And different coordination numbers lead to different structures.
Hmm.
The lectures highlight some common ones like rock salt, cesium chloride, and zinc blend.
Rock salt. Wait, like the stuff we sprinkle on our food.
Yep, that's the one. Sodium chloride. It's a classic example of an ionic solid. Its structure is super simple, but also really strong. Like, think about how much effort it takes to grind those crystals in a salt mill.
Wow, so even though it's common, it's still a powerhouse? What about those others? Cesium chloride and zinc blend. What makes them stand out?
Well, each of them represents a different way those ions can pack together, and those arrangements give them different properties. For instance, cesium chloride has a different coordination number than sodium chloride, and that affects things like its density and melting point.
Okay.
Zinc blend is interesting because it has a tetrahedral arrangement,
Mm.
which is a little more complex, but it leads to some cool optical properties.
So it's not just what ions are there, but how they're arranged in space. That's wild. But why do they form these particular structures? Is it random, or is there like a driving force behind it?
There's definitely a reason. It all comes down to energy.
Okay.
Solids, especially ionic solids, want to be in their lowest energy state possible, like finding the comfiest spot on the couch.
Ah, so they're looking for their chill spot.
Exactly. And the structure they adopt helps them get there. And one of the key things determining that energy is called lattice energy.
Lattice energy.
It's basically a measure of how strongly those ions are attracted to each other in the lattice.
So high lattice energy means they're really attracted to each other. Like a happy family, hard to break apart.
Precisely. The lectures even talk about this cool method called the Born-Haber cycle, which helps scientists calculate that energy, taking into account all the steps involved in forming the solid.
Sounds complicated.
It's a bit involved, but it's incredible how scientists can predict and control these structures, which leads to creating some amazing materials.
For sure. Okay, so far we've mainly talked about binary ionic solids, meaning they're made up of two types of ions. But what happens when we toss in a third element?
Things get even more interesting. When we have three or more elements, we enter the world of ternary ionic solids. Predicting their structures gets trickier, but we still see patterns. The lectures focused on two key structures, perovskites and spinels.
Perovskites? That sounds fancy. What's the big deal with those?
They're kind of rock stars in the materials world, especially in solar energy.
Oh, interesting.
Perovskites have this specific structure, large cation, smaller cation, and an anion, usually oxygen.
Okay.
But the cool thing is the structure is super versatile. It can accommodate all sorts of different ions, meaning we can tweak their properties for different applications.
So it's like a one-size-fits-all, but with endless possibilities.
Exactly. That's what makes them so exciting, especially for things like solar cells.
Oh, cool.
Perovskite solar cells are getting a lot of attention because they're really good at converting sunlight into electricity, and they're much cheaper to make than traditional silicon solar cells.
Wait, so they could be the future of solar power. That's huge. What kind of perovskites are used in those solar cells?
One of the most promising ones is called methylammonium lead halide perovskite.
Wow, that's a mouthful.
It is, but it's showing incredible promise in tests, almost rivaling those traditional silicon-based cells.
That's amazing. So perovskites are definitely worth watching. What about spinels? What's their deal?
Spinels are another fascinating family. They have a formula AB204. Their structure is based on a close-packed arrangement of oxygen ions, with the A and B cations in specific holes within that arrangement.
So it's like those close-packed structures we talked about earlier, but with an extra layer of complexity.
You got it. And like perovskites, this leads to some pretty incredible properties. Some spinels are magnetic, so they're useful in electronics. Others have cool optical properties, making them good for pigments and lasers. And get this, there's even something called an inverse spinel.
An inverse spinel.
Where the inner rock cations switch places, further tweaking the properties.
It's like those ions are always up to something, finding new ways to arrange themselves and give us new properties.
That's what makes solid-state chemistry so cool. It's all about understanding these tiny building blocks and how they create everything around us.
It really makes you appreciate the invisible world, how these tiny particles influence everything we see and touch. Okay, so we've covered metallic and ionic solids in depth. What about those other two types we mentioned earlier? Covalent network solids and molecular solids.
Right, we should definitely touch on those. Covalent network solids are all about strong directional bonds forming these big networks. Think of them as intricate webs held together by some serious forces.
Intricate webs held together by serious forces. That sounds intense. What kind of materials are we talking about?
Well, the best examples are probably diamond and graphite. And here's the crazy part. They're both made entirely of carbon.
Whoa, wait. Diamond and graphite, both pure carbon, but they're so different.
Right.
Diamonds are hard and shiny, used in jewelry.
Yeah.
Graphite is dark, slippery, like for pencils.
Yeah.
How is that even possible?
It all comes down to that covalent bonding and how those atoms are arranged. See, in diamond, each carbon atom is bonded to 4 others,
Okay.
forming this super rigid 3D network.
So it's like a fortress of carbon atoms.
Exactly. All holding on tight.
That's why diamonds are so hard to scratch.
Yeah.
Like you're trying to break apart a giant web.
Exactly. But graphite, on the other hand, has a totally different structure.
Okay.
Its carbon atoms are arranged in layers, kind of like sheets of paper stacked up. And while the bonds within each layer are strong, the forces holding those layers together are weak, so they slide past each other easily.
Uh-huh. That's why it's slippery and why it makes a good lubricant.
Exactly.
So every time I write with a pencil, I'm basically letting those carbon layers slide around on the paper.
You got it.
That is so cool. It's amazing how one element can be so different just by changing how the atoms connect.
Yeah, it is pretty incredible.
What about molecular solids? What are those like?
Ah, molecular solids. Those are the softies of the solid world,
Okay.
held together by these weaker intermolecular forces. Think of it as gentle attractions between molecules, rather than strong bonds.
So forces acting between molecules, not within them.
Exactly. And because those forces are weaker, molecular solids tend to have much lower melting points.
Makes sense.
And they're generally pretty soft. Like, think about ice. It melts easily because those water molecules are only loosely held by hydrogen bonds.
So it's like they're holding hands gently, not in a death grip like those carbon atoms in diamond.
Exactly.
Gotcha. Wow, we've covered a ton in this deep dive. Metals, alloys, ionic solids, covalent network solids, molecular solids. It's amazing how much variety there is in the solid world.
It is. And it all comes down to how those atoms interact.
It's like they have their own little dance creating all this amazing diversity.
Yeah, it's a beautiful thing.
And as we've learned, understanding the dance unlocks so many possibilities.
Absolutely.
We can design new materials, improve old ones, even start tackling some of the big challenges we face.
Exactly. Like developing better solar cell.
More efficient materials for building and transportation.
Yeah. Or even biocompatible materials for medical implants. The possibilities are pretty much endless. It's mind-blowing. And you know what's really stuck with me? Just how the arrangement of these tiny, invisible particles impacts everything around us. It's like a hidden code governing the physical world.
It really is. So as we wrap up our deep dive, here's something to think about. If we know how the arrangement of atoms dictates a material's properties, how can we use that to design the materials of the future?
Ooh, good question.
Ones that are even more efficient, more sustainable, maybe even with properties we haven't even imagined yet.
That's a challenge for all you listeners out there. Keep learning, keep asking questions, and who knows what incredible materials you might discover. Until next time, keep those brains buzzing.